Great, thanks. Last time there was the Hansel lemma and theorem, and let me make a few more comments. So first of all, the basic application of the Hansel lemma theorem. Just polynomial in one variable, and we can take its reduction modulo p, and then any simple root, meaning that f prime of x not 0 and f prime derivative of x not is not 0, and x 0 is in fp. Any simple root lifts to a root of f in Zp. And you just apply straightforwardly Hansel lemma. You take n equals 1, k equals 0. Okay, and for example, this solves quite a few home assignment problems. Just as a black box, you don't need to even think. But certainly it's better to think, at least sometimes. Then another application is to quadratic forms. So you consider so q over x1 and so on, xn, or maybe n is bad, like m, equals the sum of a I j x I x j, and here everything is in Zp. And it's a symmetric matrix. M by M. Okay. And suppose that the determinant of this matrix is invertible. Okay, and also take some value, and then the claim is that any primitive solution f of x is maybe modulo p, and primitive means that x1 and so on, xm, they are not all simultaneously divisible by p. So there exists I such that xi is invertible. Okay, so any primitive solution of this equation, modulo p, lifts to an exact solution in Zp to the power m. Yeah. And again we apply just Hansel theorem. again, n equals 1, k equals 0. Only we have to satisfy the assumptions of the Hensel theorem somehow, right? So what do we do? Well, first we compute the partial derivatives, and what do we get? What is the partial derivative of, well, sorry, maybe it's not f, it's q, sorry. So what is the partial derivative?
Sum over j is j.
So j is fixed.
And sum over
So over I, yes.
yeah.
Of what?
I j of sum
And then what?
xi.
And it is not quite true. And it is important. Pardon me?
There are quadratic terms.
So what? Well, they are in here. I equals j. But still?
Quadratic terms should be multiplied by q?
Right. So it's twice. And for this reason, we should assume that p is not 2. It's very important. Otherwise, you could easily find a counterexample, even for one variable. Okay, but now it's fine. 2 is invertible. And we know that the determinant also is invertible. Okay, so since the determinant is invertible, well, maybe this matrix A, so to say, is not 0 modulo p. There is j such that dq over dxj is not 0, right? Because this is the result is twice a xi. Sorry, xj, twice a xj, and this a is invertible. It cannot kill all xj's simultaneously, right? No, sorry, it cannot kill anything at all. It's invertible, and we assume that sum of xi's modulo p is not 0. So this will be not 0 either. A is invertible. Okay, so some of this xi's is not 0 modulo p, so this is sometimes not 0 modulo p. Okay, and now we apply the Hensel-Lemma theorem as a black box. Okay, now if p is 2, then we will take n equals 3 and k equals 1. Okay, so for this we assume that so if there is a primitive solution q of x equals 0 modulo 8, n equals 3, so yeah, it's modulo cube of 2. Then
Sorry,
yes.
The solution is just the solution modulo p, right?
Yes. Well, how to say? Now it's not modulo p. Now it's modulo p cube. Now it's modulo 8. So this is what I want. But primitive means that that k is 1. So we mean that some of the coordinates, there is a coordinate which is not divisible by 2. Okay? So there's, well, the same requirement for coordinates, but for the equation itself, it's much sharper. It's equality model 8. Okay, then it lifts to an exact solution in Z2 if there is certain coordinates such that the partial derivative modulo j's coordinate is not 0 modulo 4. Okay, and for example, it's true if the determinant of our symmetric matrix is invertible, just as before. Okay. So maybe, if time permits, at some point we will return to quadratic forms over p-adic numbers and over rational numbers, because it's a very nice theory, which was one of the first and strongest applications of p-adic numbers. Namely, the problem is how to classify all the quadratic forms with rational coefficients. And then it is possible, the classification is possible, and it proceeds by reduction to local problem in p-adic, and all p-adic numbers. Namely, there is the famous Minkowski-Hasse principle, which says that two quadratic forms of the same rank over rational numbers are equivalent if and only if they are equivalent over all p-adic numbers and reals. So if they are equivalent everywhere locally, then they are globally equivalent too. And then it is possible to thus we classify the reduction problem to all the p-adic forms, and then it's possible also to solve it somehow based, for example, on this.
Great forms, you mean?
That you can change a base, and one matrix will become the other.
So what direction of
Just GL, yeah. So if you the change of matrix base is C, then A will go to C transposed AC. Okay. Probably you know this from basic linear algebra class.
One of the C's be to the power of -1?
No. For linear operators, yes, but for bilinear forms, just this.
Okay, yeah.
Okay. Okay. Yes.
Who is K here?
Who is K? K is something from the statement of Hansel theorem. So you want your solution to be to the order of p to the n, like 2 to the n, but you want your derivative not to vanish too much. Your partial derivative not to vanish too much, namely here. Pardon me? The order of vanishing of some partial derivative must be. Okay. So now I promise to tell something about the comparison of p-adic numbers ZP versus like FQ of T for formal power series, Taylor series, and they are very, very similar to each other. So these are the corresponding local fields, and in fact, there is a complete classification. So locally compact fields. Well, complete with respect to non-trivial norm. They can be fully classified, and they are either real numbers or complex numbers. Those are Archimedean cases, or say local functional fields. Of characteristic P, positive characteristic, or else some finite extension like Q. This P is supposed to be maybe math-frac P, German P. Like this. Okay, so this is a local arithmetic field of characteristic 0, but residual characteristic P. Okay, there is nothing else, nothing more. All the local fields, so locally compact complete fields, they're like this. There's nothing else. And so, well, these have characteristic 0, these have characteristic P, but the analogies go much further and deeper. Okay, so this is well, in the general philosophy of like numbers versus functions. So the real well, how to say, God-given numbers are just integers, and not p-adic. P-adic is some completion, and the real functions are maybe functions on some curve, maybe over finite field, maybe like this, like rational functions of one variable. That's a typical field. But now there are many norms. Well, maybe if I have a ring here, I want to have also a ring here like this. But then if I... Yes.
What was the finite extension of QP? What was it about?
Here?
Yeah.
It's just the complete list of local fields.
Okay, so
A local field of characteristic 0. And local means locally compact, complete with respect to non-trivial norm. And if it's of characteristic 0 and non-Archimedean, so if it's Archimedean, then it's either one of those. If it's characteristic 0 and non-Archimedean, then it must be a finite degree extension of p-adic field. We'll talk more about it later today and next time.
What is the norm series of finite field?
Here. Mm-hmm. Yeah, it's interesting. So, well, it's certainly it's always p to the power.
It's better not to write here.
Not to write here. Okay. So the norm in non-Archimedean case is always p to the negative valuation norm of a series, for example, like f, is p to the negative order of f. And what is, the question is, what is order of f? What is it? Any suggestions?
How much is divisible?
Yeah, it's just the order of vanishing at 0. I mean, for the field of Q or T. Yeah, if your series is the sum of I t to the power I, and I is, say, bigger or equal to certain n, and an is not 0, an is not 0, then the order of f is this L. Okay? So it can be negative, then the norm will be big. If it's positive, the norm will be small. Okay? Fine. So this is the norm and topology on the local functional field. Pardon me?
What is the completeness with respect to a non-trivial norm?
That any Cauchy sequence has a limit. Just the usual, the usual definition.
What's the trivial norm?
Trivial norm, I think it's equal to 0 for 0 and equal to 1 everywhere else. Discussed this last time. What is so similar about those things? Well, for example, both guys are principal ideal domains, and any prime ideal is maximal. Okay, and yes, both Z and F, Q, T are principal ideal domains, and any non-zero prime ideal is maximal. In fact, the collection of all such ideals is called the spectrum of our ring, this or that, and also these guys are called points. Why points? Well, if we consider, say, like this ring, then its maximal ideals are just numbers. Okay, so the points of the line. And this terminology persists in arithmetic as well. So the points of Z or spec Z, they're just 2, 3, and so on. But then you also say that there are infinite points. According to Ostrovsky theorem, namely, in this case, it's R. One more completion that means this way. In this case, we miss nothing else. Sorry, we do miss something. There is valuation. How to say it? I don't know. Maybe on the. there is no ideal here, but if we go to the field like this, then there will be the infinite point. Yeah, the order of vanishing at infinity. So maybe I should say infinite points of Q. Then there is this. Oh, I shouldn't have written there. Yeah, I'm sorry. Pardon me?
Order at infinity, you just
The order for a rational function. Well, you can take uniformizer T inverse and say the same. Yes.
Repeat again what are the infinite points and in which spectrum they are like.
Well, for any field, say global arithmetic field, K is just a finite extension of Q. And then the infinite points are the well, isomorphism classes of embeddings of K into reals and embeddings of K into complex numbers, but modular complex conjugation. Because those give you the same norm, the two complex conjugate embeddings give rise to the same norm. Pardon me?
So we're not talking about this ring spectrum right now.
All the points they are the points of the spectrum of OK. This is the ring of integers. Okay, union those infinite points. Okay, so at the moment there is no theory that would treat them uniformly. So you just formally add those. It's called Arkelov geometry when you also consider those points. But points are just argot for slang for all the norms, or the classes of norms. Okay, so what we're talking about? We're talking about the points
What's the definition of
Pardon me?
What's the definition of OK?
OK is the integral closure of Z in K. So the solutions of all, you know what it is? Okay. So the points of this field F Q, say of T, they are infinity plus all the monic irreducible polynomials. in fq of t. Right? It's like with the usual integers. We had just prime ideals of the ring Z and also some infinite point. Now, for the functional fields, they're of characteristic 0, so certainly there are no Archimedean norms, and all the completions will be non-Archimedean. So they're all treated on the equal footing, but well, they correspond to the prime ideals in this ring, and also there is one more evaluation corresponding to the infinite point at projective line. Okay, so this is the analogy between the characteristic 0 case and characteristic p case, functional field and a global field. Okay. So in this sense, this situation is more interesting, because over complex numbers, when the ground field is algebraically closed, all the irreducible polynomials in one variable were just linear polynomials, x minus a. And they were numbered just by the points of the ground field itself. But since the finite field is not algebraically closed, then it's more interesting. But in a sense, you can reduce to the algebraically closed case, namely, you can first extend scalars to the algebraic closure of finite field. So prime ideals of fq bar of t, they correspond to polynomials like t minus a. A is any point in fq bar. But then I have to somehow return back to the finite field. So how can we return?
What is FQ bar?
FQ bar, the algebraic, well, an algebraic closure. No. Maybe it's a useful abstraction, but maybe you don't really explicitly know what it is, as opposed to complex numbers, which you are trained to know from your childhood. So, how to classify the monic reducible polynomials over finite field from the point of view of its algebraic closure? Well, you know that there is the Frobenius automorphism from fq bar to itself, namely x goes to x to the power q, and then the fixed points are exactly the finite field fq itself, and then it acts, well, on this field. Now the orbits of Frobenius, so say fq bar divided by, say, Frobenius to the power z, the orbits of this, they are in one-to-one correspondence with the irreducible monic polynomials. So prime ideals in fq of t. Right? Namely, given an irreducible polynomials, you consider all of its roots. This will be a Frobenius orbit. P of x goes to all roots of P in this algebraic closure. And conversely, given an orbit, how do you construct a polynomial? Just if you believe that this direction is correct, then how do you describe the inverse direction?
I don't think this direction is correct yet. Why would an orbit be over roots of random polynomial?
Why they are all conjugate under Frobenius action? That's what you ask? Why all the roots are conjugate?
Conjugate, and why they are conjugate only with each other?
Well, maybe by some Galois theory, you take the extension of this finite field given by this polynomial. It's an irreducible polynomial.
Okay.
And then you know by Galois theory that they are all mixed by Galois group.
And the
That Galois group is generated by Frobenius.
Yeah, I forgot.
So there you are. And conversely, given an orbit, how do you construct a polynomial? An orbit O in FQ bar goes to P of x equal to P of t, sorry.
The name of polynomial of
Any of them, yeah, but maybe more explicitly, it's just the product over all x in this orbit, t minus x. Yeah. Okay. Fine. So we described all the points, and
to check. So we could actually count this reducible polynomials here. So
in a sense, yes. For example, for a given degree, yes, certainly. That's a
it's
nice problem.
it's a nice problem. So well, and then how do we decide the equivalent under Frobenius action? So we.
It's just what Masha explained. It's some basic Galois theory, plus the knowledge of Galois group. The Galois group of any finite extension of any finite field is generated by Frobenius.
So
But you know that all the roots of an irreducible polynomial are any one root can be taken to any other root by the action of Galois group.
So maybe I should think.
Okay.
I'm sorry.
Okay, yes.
I had a question. So we are
Yes.
considering points in the field, right?
Yes, but by points you mean the equivalence class of norms
So
or evaluations, in other
prime
words.
ideals anymore.
Prime ideals well, your field is the fraction field of certain ring, or namely a ring of polynomials. And then turns out that the points in the field are, well, at least in this particular case, there is one infinite point which corresponds to the infinity point. And all the other correspond just to the points in the spectrum of this ring.
And these points are somehow connected with the norms.
Yes, so that's what I want to say. That given an irreducible polynomial p of q of t, the corresponding valuation ord p of f is the maximal power of p that divides f. Yeah. So our ring is Euclidean, if you wish, or whatever, with a unique factorization domain. Okay, so it's all very similar to the p-adic numbers. How did we argue? We took any a over b in rational numbers, and then we wrote it in the form p to some power, I don't know, n times a prime over b prime, and those a prime, b prime were prime to p, right? And then we said that the order at p of a over b is the n, this n. Yes, this was our approach. And the p-adic valuation of a over b was p to the order negative. Okay? And this, we do just the same here. So we replace this small p by this capital P. Just the same, right? And I'm supposed not to write here. Okay. So the complete classification of norms on this global functional field is those indexed by irreducible polynomials, monic polynomials, and one more, just one more, corresponding to the point infinity. And what is the order of vanishing at infinity? Say for so if you have polynomial f, then what is this order of infinity of f? What is the order of vanishing at infinity? Right, it's just the degree of f, yes. So the infinite adic valuation is just p to the negative degree. Fine. Now, the local ring itself and the local field, they are very similar to a p-adic integral or rational numbers. Is very similar to p-adic numbers. In what respect? So this is the limit over z modulo p in z. And what is this? In the same vein, it is also the limit of something. Of what?
Is there a square bracket?
Here it's square bracket, yes, absolutely.
If you take the degree of f to the infinity, like f cubed.
So the limit of what?
Polynomials of a given degree?
No, these are rings. So you want some rings. You want some quotient rings of the ring of here integers, here polynomials.
Maybe the same, but you
Yes.
keep the end.
Just this. Okay, so well, they are very similar. Also, if you remember, QP was the limit, co-limit of such limits. And well, here too, you can I mean, you have embedding not only projections like this, you have certainly fq of t modulo t to the n projects to fq of t modulo t to n minus 1. But also there is an embedding in the opposite direction. Okay, and well, this is used for this limit, for co-limit. Okay, and now what is the well, you see, when I said about the classification of local fields, I said that in characteristic P they were all like this. So the only thing which matters is the cardinality of the residue field. Okay, nothing else. Whereas in characteristic 0 there were many more. So you first specify some prime number and then take some finite extension. Looks there are many more, but in fact not really. I mean, you can take any irreducible polynomial p and then you can again consider the inverse limit of our ring of polynomials modulo the powers of this guy. So if our polynomial p is just t, then that's what we get. But we could also consider this. This will be a more straightforward analog of all the possible p-adic integers. But then I claim that this inverse limit is absolutely isomorphic to f q prime over maybe t prime. Pardon me? What is q prime? Yeah. So q prime is the cardinality of the first quotient. So the first quotient will be a field. It's a field. Okay, and then, well, if you wish, this t will give rise to that t prime, or maybe no, maybe how should I say this? I mean this. Okay, so if our ground field was algebraically closed like complex numbers, then p would be t minus a. Right? And this is our point A. And then the inverse limit of polynomials modulo the powers of t minus a will be certainly isomorphic to C of t prime, where t prime is t minus a. I mean, you need some uniformizer that vanishes at this point. And the same here. This t prime is, well, maybe I should say t prime is p, in a sense. So it's something which vanishes at the zeros of p. So it's p itself. Okay. Yes?
Reducible polynomial,
Yes?
we would also would like to see it as a affine variety.
What do you want to see as an affine variety?
I mean, by reducible polynomial, we look at the solutions, right?
Yes, it has roots in the algebraic closure.
And no, I didn't. So
Okay. Yes, so in case our field is algebraically closed, it's all very straightforward like this. But in case it's not algebraically closed, you need to choose some uniformizer in a more clever way. Okay. Now, certainly you can also consider Adels over a global field like this, rational functions. So there's the restricted product, over all, well, let's say infinity and irreducible polynomials, just all the points over P1 of FQ, just say Frobenius orbits. In P1 of FQ bar, if you wish, of the corresponding local fields. The local fields will be, well, I don't know, you take FQ of T and then you complete it with respect to this norm P or infinity. Okay, but you know that any such completion will be absolutely isomorphic to the local field. Okay, so this is called the Adel ring of our field, and then there is this embedding of the global field into its ring of Adel. And what does it do? Well, it takes a function f and associates to this function all its Taylor expansions at all the points. Okay, it has a few poles, finitely many poles. There, the Taylor expansion will be a Laurent series. Everywhere else, it will be a formal power series without poles. Okay. To the collection. It's Taylor expansions. At all the points of P1 of FQ. Okay. Okay, maybe one last thing I want. Oh yeah, the same. So you solved your home assignment that the embedding of rational numbers into Adel has discrete image in the restricted product topology, and the same is true here. Certainly, the induced topology on the global field by the restricted product topology here is discrete for evident reasons. And by the way, I didn't formulate this problem in the home assignment, but what is also true is that this quotient is compact. And if you solved the home problem about discreteness, I think the same solution gives this I mean, you must have produced an open subset which contains only point 0 of Q in order to prove the discreteness, right? And now, if you and this open subset, I guess, is compact. So now, if you increase it a little bit, it will cover the whole quotient, but it's still compact. So this is, you get this for the same price. Okay. Now, the ring FQ of T of formal power series, just as a ring, is something pretty simple, maybe simple-minded. I mean, you just write any power series as well, A0 plus A1t plus A2t squared plus so on. So it has coordinates A0, A1, and so on. And the ring structure is, well, you take A plus B, and what do you get? What is the zeroth coefficient of the sum?
A0 plus
Yes, A0 plus B0. And what is the first coefficient? A1 plus B1, and so on. Well, if you multiply, then it's not as stupid, but still, you know that it's A0 times B0, and then A0 B1 plus A1 B0, and then so on. So it's pretty straightforward. Now,
May I have a question?
Yes, yes.
This,
Yes.
So you said that it's restricted product. So
Yes.
does it mean that the almost all points?
By definition of Adel, yeah, the Adels are defined as restricted product. So almost all the points are in Taylor series, not in Laurent series. Only finitely many are allowed to have poles,
Okay.
by definition. Okay, so now guided by similarity between p-adic numbers and formal power series, I want to ask how it works for p-adic numbers. So again, we can write some A in p-adic numbers as again an infinite sequence of its digits. AI, well, say in the finite field of P. And we want to write down addition and multiplication in these terms. Well, it turns out that you can solve this problem. It will be harder than, not as simple-minded as they are, but possible to do this. Only you have to find these digits in an intelligent way. Yes.
What is the problem? We just take a sum and modulo sum p over.
Yes, but you somehow want this to be certain operations in FP. Well, like here you had either a sum in FQ. It was very stupid, or such an operation in terms of coordinates in FP, and you want again this to be some operations in FP.
So the problem, if we just think in integer terms, is that these things can be bigger than p and thus give not the same thing in FP that they give in integers.
Yes, for example. And what I'm aiming at are the Teichmüller representatives that you had in your home assignment. So the intelligent way to define digits is via Teichmüller representatives. So we need the Teichmüller representatives. Namely, this is F. Well, we have, I don't know how to say. Well, we have FQ with multiplication. There's a section, so to say, into ZP with multiplication. Okay, so 0 goes to 0, 1 goes to 1, but the other guys, I don't know, well, xi's go to xi's tilde, something like this. Okay? So they go to the roots of unity. Xi tilde to the power q minus 1 will be, it's p. P minus 1 will be 1. Okay, and then we use those to define the digits.
FP?
Oh, sorry, here is P. Yes, thank you. So, any x or any a will be written as I don't know how to say this. X 0. X0 tilde plus p times x 1 tilde plus p squared x2 tilde and so on. And then to this a we associate this sequence x0, x1, x2 and so on in fp infinity. Okay? So we just decompose any p-adic integer in this Teichmüller basis, so to say.
What are the differences between xi's and xi's with tildes?
So xi's are just numbers in the prime field, fp. And these are their lifts as roots of unity into p-adic integers that you had in your home assignment.
So
xi's are in the prime field of characteristic p, and xi's tilde are in p-adic integers of characteristic 0.
So these are just representatives that ends on xi, right?
Yes.
Okay.
What you had in your home assignment?
I don't understand.
Yes.
What is x, this index p plus 1 tilde? We have only pi representative.
I'm sorry. How should I say this? I don't know. Maybe I shouldn't write I here, just like this. So this is in FP, and this is in ZP. Okay, and now I decompose any p-adic integer as some Teichmuller representative, like here, then p times another Teichmuller representative, like here, p squared, like another representative, and so on.
I'm sorry, but won't this integer really ends on 0 always, no? Because if 0 ends on 0...
No. I'm sorry. Just any x, I don't know how to distinguish. Any element in the finite field lifts to a p-adic integer. And we don't really need 0, maybe, because it gives nothing. So any, well, for example, suppose, yes.
Просто вложение поле или это именно...
No. They're just digits. So because the addition does not go to addition, only multiplication is preserved. As opposed to there we had some simple operation for addition, but something less simple for multiplication. Here, vice versa. The multiplication is very straightforward. They're multiplicative representatives. But, well, it's similar to here. At the 0th level, multiplication also went to multiplication.
Да, но
But then, yeah.
вопрос скорее про представление. Ведь все эти иксы, они заканчиваются, ну, условно, на их соответствующим элементам в p, правда?
Да, yes.
Ну, то есть x0 заканчивается на ноль, условно. Ну, то есть тогда вот эта штука, если так записать, она всегда...
No, this is just the...
Смотри, это координаты. У тебя написано в координатах, которые бывают, принимают значение, как вот эти корни одиночные корни вниз.
x0 minus a is divisible by p. So I find the first digit. These are digits of my p-adic integer. I define some clever way of writing the digits. The first digit is the representative modulo p.
Okay.
It's something very straightforward. But the first digit is defined like this. So you...
Сейчас, это разные? Тильда и бар это разные?
No, they're all tildes.
Я понимаю, что такое просто запись в личной системе счисления, но вот это то же самое или нет?
No. But
Просто тогда непонятно, что происходит, потому что как будто бы у нас вот эта сумма, она в плане вот именно суммы в поле p-адических чисел, да?
yes. Because these guys are all divisible by higher and higher powers of p, so this will converge in p-adic.
Да, ну вот еще раз, то есть тогда не любое, наверное, такое, можно так представить, да? Или
No, any. Well, if a is divisible by p, say by p, then this will be 0, but there will be something here. If a is divisible by p, then its first two digits will be 0, but there will be something non-trivial.
вот x0 с волной, это не 0, просто еще раз уточню.
Нет, смотри,
Yes.
это координаты. В принципе, это, да, это координаты.
Those numbers are just correspond to those numbers of your coefficients in t. This is the most basic, the first digit. It can be anything. Can be 0, can be 1, can be anything at all.
Переменная, вот x0 с волной это переменная?
It's a Teichmuller representative.
So it's some fixed.
Some fixed Teichmuller representative, yes, depending on A. There are p many Teichmuller representatives,
Yes.
and given an integer A, you find the first one as the one which is equal to A modulo p.
Okay.
Then you subtract it, divide by p, and continue like this.
Все, понял.
Okay, so you obtain some sequence of elements in the prime field. Now the point is that you can write down both multiplication and addition in these terms. There will be some given by some universal formulas. For example, for multiplication, it will start again with multiplication. The claim there are certain polynomials such that xi over well, I don't know, maybe let's call it a sub x, a sub x plus sorry, that the ith coordinate of ax plus ay is well, some polynomial f I of x0 and so on, xi, and then y0 and so on, yi. Polynomial of 2i plus 2 variables. And the same for product. Okay, and this construction, once again, this construction somehow takes the prime field and produces something which gives you p-adic numbers. So you work with infinite sequences of elements of prime field, and you somehow learn how to add them and how to multiply them. This procedure is called the width vectors. And your next home assignment will be about width vectors. So how to write down such polynomials which produce from fp that zp. And in fact, it works not only for prime fields, but for anything at all. You can, so given such polynomials, you can plug in coordinates anywhere at all. In a ring, in a bigger field, whatever. So it's called the width vector construction. But somehow I exhausted all my time. It's hell. This was only a side comment, so the topic was absolutely different. Sorry. Okay, so maybe I'll give some preview trailer of what will happen next time. So next time, we will start the Tate construction over complex, so to say, p-adic field, meaning that p-adic numbers, as we have already seen, they're analytically much simpler than real numbers. I mean, the non-Archimedean topology is much simpler than the Archimedean real topology. So it's totally disconnected. But in return, it's much harder with respect to arithmetics, namely the complex numbers or real numbers, they're algebraically closed or almost algebraically closed, but p-adic numbers not at all. as you have seen. Many equations do not have solutions in QP. But you want to have an algebraically closed and complete field. So, well, you will go to some algebraic closure of QP, and then we will spend some time, next time and maybe one more, arguing that the p-adic norm allows a unique extension to this algebraic closure. Okay, and then and then, unfortunately, this algebraic closure is not complete with respect to this extension of the norm. So you have to still complete it. And this will be already algebraically closed. So nothing more is required.
We took the algebraic.
First you take algebraic closure, then it's a deep and important theorem that the p-adic norm extends uniquely to this algebraic closure, but this algebraic closure is not complete with respect to this norm, extended norm.
So Q, if you algebra.
Well, Q is not complete itself, so no wonder. But this one was complete. But after you take algebraic closure, it's not complete anymore. So you complete it. And this is already algebraically closed.
The one that has the hat,
Yes.
it has to have P as an index, right?
Oh yes, certainly. Yes, thank you. Mm-hmm. So we'll start this construction next time. And this field is very, very similar to complex numbers. I mean, it's non-Archimedean, but it is algebraically closed and complete. So you can do well, algebraic and analytic operations there easily. And that's what we'll do afterwards. Okay. Thank you.